Alright, it's that time again. Welcome to the weekly live stream. This time we'll be going over river propagation because that's what I'm neck deep in this week. So, let me go ahead and thank the patrons. Really means a lot to me. This year, apparently I made just enough that I'll have to treat it slightly different tax-wise. So I should hopefully break even on server costs this year because of you guys. So thanks a lot. And so let's go ahead and get started without too much more fanfare. So first let me talk about last weekend I played with region mapping, which is kind of I'm back in the mapper tool playing with fractals and stuff. And did some work embedding the tool over on the Mythruna side so that I can do more rapid development over there. But before I did that, I played with regions, which I'll show you what I mean in a second here. Come on. Yeah, so standard tool that you guys are used to seeing. Of course, it's flaking out here for a second. Yeah, it's the spawn location of this particular map. But the see if we go up here, regions, I think I have it turned off. Draw regions, process regions. First of all, yeah, let's go ahead and do that. So it'll take it a while to generate this, but the idea being that it goes through and looks for bodies of land, bodies of water. In this case, I think I'm looking for trees and deserts and grass plains and then marking them as regions. This will all factor in later into, potentially, yeah, so here we've got, that's marked as one solid forest, and then we've got a couple smaller forests here. This is a giant desert area. The idea behind being able to detect these regions, and certainly for detecting, we don't see it here, but it'll also do the oceans and the land masses. But the idea being that if I was to randomly generate lore, I can give these different regions names and have NPCs and things or books refer to them. As you wander around the world, you could hear about some desert off to the east. Say you're wandering around here, there's some town that talks about a desert across the ocean because the world would know these sort of facts about the world. And so I got started in that and played with that a little bit, and you can see it even crosses boundaries appropriately, which was kind of tricky to get working. And then really what I wanted to do though is work on rivers, because rivers are super important to everything else, town placement, trade routes. Rivers turn out to be a pretty important thing. And so what I did was all of these sort of moss tools, like the mapper and the shaper and different things, can be embedded in, so these are the open source tools. They can be embedded in other projects, which means that those projects can, the tool can then access that project's classes and code. So I've embedded it over into the Mythruna client so that I can run the mapper directly over here, and it would have access to the Mythruna fractals. And as I code up the river propagation and stuff, I can embed that directly. Right now it's still in scripts, and I'm going to go over here and turn some things off so we can kind of see how I built it up. Let's go to the rivers. So we want to draw cost, draw seeds false. Where's the one where I can say draw samples? Sorry guys, I meant to set this up ahead of time and I lost track of time. So yeah, let me find where my add markers. There's somewhere I add all of the, maybe it's over here. The draw grids, yeah. Draw metadata, true. Draw the metadata, and over here, draw seeds, false. And for now, we'll just say if true, return. Okay, so run the mapper tool. And so one of the problems before was every time I edited one of the fractals over on the mapper side, then I had to transfer that edit over to the Mythruna code, and that wasn't always a one-to-one translation, and so getting the world to match, you know, when you log into the world or run around in the world, getting it to match this map was sometimes kind of tricky. And this tool now directly embeds the mapper tool, or the Mythruna now directly embeds the mapper tool, so we can be sure that we're using the same fractal because it's actually using the same Mythruna fractal. So here we've got we've collected some metadata related to water. In this case, water, and so this is kind of showing the wetness and the vegetation level of these different areas. So the green is the vegetation level where trees or plants would grow, and the water is sort of the precipitation level. In this, it collects samples every 128 meters. It's just a nice demarcation. We don't need to be exact. In fact, being inexact is better for randomness, and that's a deeper discussion. But you can see over here we've got, you know, very low vegetation, very low precipitation. And so some of this, the precipitation for sure, is the basis for the river algorithm. And so because this is in the mapper tool, I have the ability to sort of turn this stuff on and off. So I can come over here and I can say we don't want to draw the metadata anymore. And so we don't draw the metadata. But what we do want to do is we want to process the rivers, but I only want to generate the, excuse me. One thing I did was, well, I wanted to start with talking about where rivers would likely start, and I thought that I had set up something that would render them all out. Yes, here it is. And then we want to make sure so we don't want to do any other processing. I just want to render out return. Actually, we're in a loop, right? Yep, so we'll just break, continue. See if it likes that. Yep. Okay, so it's processing all of the different cells we're dealing with here. These are not the values I expected to see. So this is a sort of flow direction. That's not really what I wanted. Somewhere I render draw seeds. So let's just put these up here for a minute. Without considering threshold. So what happens is we go through, so let me talk about what the code is doing here. We generate these sort of flow cells for each of the, you know, sample points, where we track some things like elevation, you know, what its precipitation level, what its temperature was. Scale has to do with the slopes. If we detect that we're downhill in certain areas, we set the slope for that, and the scale is sort of how water would propagate from that particular cell. And we keep track of like a slope, just a general kind of flow, and some costs that we'll talk about in a second. And then a flow cell target, so as it's when we actually start generating rivers, we keep track of which cell flows into another cell. But what we first do is we go through all of the samples and we kind of we build this sort of array of water, and so we sort of model precipitation and as it flows into different cells, so that from a particular cell we can see how much water would flow into it from surrounding neighbors and their neighbors and so on. So we build this up, seed it, and then run a propagation algorithm that kind of this is calculating the slopes. This is building the distances. Okay, so it runs through a certain number of passes of basically feeding water into the neighbors and keeping track of that. And so we build up levels of, you know, how many things fed it and how many things how many things fed it, and then how much actual water sort of flowed there based on precipitation. And that's what this loop is doing. It goes through all of those, and based on certain thresholds decides, yeah, that's going to be a potential source of a river. But what I'm going to do first is just draw all of the seeds. Draw haha, it's not, I mean, it's just stupid flow. Like, this elevation is lower than this elevation, so something would flow there. Let me see if I can show you what I mean. Draw potential seeds, true, and then look for draw seeds. So draw potential seeds. Oops, I already had the seeds. Where did I do my? So we ought to be able to return right after this to make sure we don't do actually any river propagation, because it looks ugly right now. Oops, this could be continue. Draw potential seeds. Yeah. Why boolean draw potential seeds? Draw potential seeds. Why is that a unexpected token when it was fine here? Oh, equals dir. And yeah. Spell it right. Okay. So now we're back to something that I can demonstrate. Here we go. I gotta get rid of those pink things. So, okay. Here we go. So as we look at these different samples, the blue is how much water flowed into that area from surrounding cells, and the yellow is sort of a normalized factor for how many surrounding cells fed it. So in this case, we see the water level's fairly high. The feed level is also pretty high, probably because it was fed from each of these surrounding cells, because they're all slightly higher. Notice that there's a dip here, and we don't pay attention to that because we are loosely sampling every 128 meters. So we miss some details in the terrain, but we're just trying to get an approximation, because the actual detailed river flow will follow the terrain, but we're just trying to get like a general idea, something that can be computed in a time that would be useful for world generation. We can't go off computing a world for an hour, right? We've got to have it a few seconds here and there. And you can see I'm generating all of this stuff along with a bunch of other data that I'm not displaying at the moment for this huge area of land. I mean, each of these squares is, you know, basically 16 kilometers. So, I mean, each of these big hexagons is about a day's worth of Mythruna travel, daylight, you know, sun up, sundown, sunrise to sunset, to walk across this. And so you can see this is a large area of land. These are all you know, samples. Finding right level. Yeah. And the thing is, like, if I use lower level of detail, then I potentially get more interesting terrain in the end. For example, if if sampling says, like if my samples were even wider and it says, hey, this river can actually flow from here to here right through this mountain, then the river algorithm just has to take into account that it has to carve a gorge there. And so if I had used an even fewer samples, we get rivers have to do more interesting things to propagate. But there is kind of a balance there. We want it to look sort of realistic, but also do some cool things that are unexpected. And so finding the right sample size is kind of fun. I used 128 meters because I've got to balance that across 100 things. It's also convenient because in a 16,384 square tile, 128 meters means there's also 128 samples. So it's just a nice round number, and it appeals to me in that sense. And I use that for a region calculation, in which case lower samples is better for finding regions. We'll use that for town seeding, where a town, anyway, it's just a good number. Okay, so here we get a place where lots of water flowed into here. So these guys got water from all these surrounding areas, and then they fed it into these, which is why the water level is so high, but the feed count's not particularly high because all these surrounding things. There's a multi-level propagation that happens. I do 2 iterations. It turns out more than that doesn't really change the picture. It's somewhere I can say how many iterations to do. Yeah, so here are iterations. If we change this, so 2 iterations means that it's going to go through one pass where it flows everything to neighbors, and then do another pass where it flows all those to their neighbors, adding to the original. And 2 seems to be a really good compromise from time and so on. It gets a pretty good answer, and additional passes don't seem to affect the ratios much. Like if I change this to 4, doubling it, and we let it calculate, it takes a lot longer, twice as long, to do that particular step. And in the end, the ratios aren't really any different. I mean, we've got a lot spikier data, that's sure, but this related to this is not that different. And as it turns out, because I want to be able to create rivers up in the mountaintops, we want to have relatively low thresholds anyway. The one I always use is over here because there's this string of high water value things up here in the mountains, and I like it, so I use that kind of as my threshold basis for what a river source would be. Is if I can get a river source to form right here, basically there's a thing, if there's enough feeding cells, if the yellow bar is high enough and the blue bar is high enough, then it's a potential river source. And there's some factor I can multiply in based on elevation that says it's more likely to happen up in the mountains. Basically the requirement is lower, because I really would like to have waterfalls and rivers that come from up high in the mountains and flow down, rather than just all sort of rivers that flow through the plains. So 2 seems to be a pretty good compromise on the number of iterations to calculate flow. Already there's water levels built in. For a given block, it can have 8 different water levels, and then it'll dynamically sort of level them to their neighbors. And each block also keeps track of flow and pressure. Yeah, exactly. So each block also keeps track of flow and pressure, so it knows kind of which direction water is flowing. That way, if I do have a really long river over like flat plains, gravity-wise, the level of the water is all the same, but the river will know that it's flowing south, for example. And so the water will look like it's flowing, because rivers are kind of an actual entity. It's not just a single water block. That water block knows it's part of a river, and that'll factor into different things later. But that's sort of advanced. So anyway, we're back to the 2 iterations, and you can see I still have enough spikes to sort of determine where there's lots of water and where there's little water. And so then we come down to, we've got these, I had to draw all the seeds. But now if we look at what just the candidates are, so I turn off this and I turn on to draw the seeds. So this is based on the thresholds. We see that rivers would start potentially here, 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 along the plains here, or where high value. So these are all potential places for a stream to start that could turn into a river, right? And as we get drier, we see fewer of them. If we go way over here to the dry plains, we see almost none. In the desert, there would be none at all. So a creek might form here and flow for a while, or maybe we actually get a real river. That would all have to be randomized, and that's what we're working on now. So the other thing I did was, when I originally started working on river propagation last year, I did an actual A-star. When I decided, if the algorithm decided, hey, I need a river source here, it would use sort of standard pathfinding to decide, okay, well, we flow down here, and there's a cost associated with going a little over the lip here, and we flow down to the ocean. This time what I did was I calculate a sort of cost for reaching the ocean, kind of like if you're on the seashore, it's 0, and as you go away from the shore, it adds to the cost. And if you go up a hill, if you go up a hill, it doesn't add to the cost any more than regular distance. But if you go down a hill, it adds to the cost because it's that much costlier to get to the ocean. And actually, let's show those. Let's show the costs and in relation to the seeds. So this will be like red spikes and pink spikes, I think. Yeah, so big, tall, red spikes. Oh, I got my cost multiplier super high. So hold on, let me turn the cost multiplier down to just 1 for now. So we come in here and we can see these areas in here, the cost is much higher because if the distance to the water is not that far, the pink values, let me drill in here. So the pink values are showing sort of direct cost. This is how many sort of cells we are away from the nearest body of water. Whereas the red value, the red spikes are showing cost. And because from this particular point we would have to go uphill to get to the water, the cost is a lot higher. And so down here, we don't have to go uphill as far as the spikes are lower. We're more likely to go this way than this way. And the neat thing about this is once you have it from any given position, if you just always head in the direction of lowest cost, you will find your sort of closest path to the ocean. And that is nice to have in your hip pocket, but I will show you that it generates some very strange, they're very uninteresting rivers. So if we take all of those sources, let's go back up here and turn off the costs, and we'll go ahead and calculate the flow. And so this is taking all those seeds and figuring out their direct path to the ocean. So kind of cool, but not usable. And for the moment, ignore the fact that all of these are straight lines over 128. In reality, these would be guidelines for the real river propagation algorithm. So if we know we had to start a river here, then we do a real pathfinding here, but we're guided by this path. So instead of trying to A-star or you do pathfinding all the way to the ocean, we do pathfinding that tries to fit to this line but can go around it and so on and so forth. So we figure the lowest cost carving that we get through here, and that'll be the next step. First I have to figure out what the sort of rough paths are. And so this is not bad in that sense. It's just kind of dumb. Like here we would expect these to kind of flow into one another instead of creating all these parallel lines. And so that's kind of lame. We also get cases where would what make sense with gravity? I read the comment late, so I'm not exactly sure what you're referring to. But yeah, here's a direct flow example that's bad, right? From this perspective, the lowest cost of the ocean actually has us go over the mountain, despite the fact that we've given high cost to going uphill. It's very low cost once you get over the hill, so the total cost is this is the best way. If we went a different direction, we would have to go way around here or way around here. And so, from a pure cost perspective, this is the quickest way. And I could carve through the mountain. Yeah, it wouldn't. Exactly right. Yeah. But I could carve, right? There could have been, for some reason, a gorge carved through here. It's just in some cases it looks a little ridiculous. So we can't use just this. In fact, I only did this piece, this afternoon, like 4 o'clock or so is when I implemented this just to see what would happen. Prior to that, I was doing quote-unquote smarter things. So if we do a straight cost check, but only, so let's say we use gravity first. So this particular source would want to flow downhill, but if we get to the point where there is no downhill, like everybody's at basically the same level, then we'll use the ocean costs, right? And so that's what this is, right? We could do, we're going to do a cost check, and we'll do a water check. No, I'll take the water check out for now. I'll explain what that is in a second. So we're not doing cost only anymore. This was cost only. Ignore everything. Just use the distance to sea cost. Now we're not doing that anymore. We're only going to do gravity, and and by the way, if they're the same level, then we'll try to do the sea cost. And so this is what we'll end up with. Give it a second. And so we get sort of, anytime it's red is where something got stuck, it didn't know where to go. And so we get more interesting rivers and things. We get some kind of cool meandering paths here. This is kind of neat. These two tributaries, became this river, which joined this tributary and came in here, and these two kind of also fed in there. And it's kind of weird that these big long rivers would flow into this little body of water, but there's only so much I can do about that without factoring in the bodies of water, which I do hope to do later. So the idea would be you find all of the major bodies of water. Currently I'm just saying if it's less than sea level, it's water, then we can flow there. But really you'd want to map the bodies of water and only let major rivers like this flow into large bodies of water if you can avoid it, or if you can manage it. Otherwise you would want to grow a lake here or something. But my problem with this, just as it stands, well, for one thing, things get really stuck. And like this, over here, we've got this, the red, it came down the hill, it stopped here. But realistically, the water seeds are determined by sort of the flow that fed into them, which I just described earlier, which was the samples with the yellow and the cyan lines. If we exceed some threshold of feed count and water precipitation level, water level, flowed in water level, then we consider that a seed. Which is why this one got, because it's in the little valley here, so it got precipitation. It's in the valley here. This particular seed up here is what I'm talking about. This became a river seed because all of these surrounding things were feeding it water. This is a high precipitation area, and so that became a seed. And to me, this would flow down and potentially have enough force at this point to come out of this little valley. Like we might, it might have carved out, it might have created a lake and carved out. So there's the other thing that I keep track of, which is the sort of general flow direction. And so one factor I have not implemented in this particular version is when we get to these areas where we don't know anything better to do, we could jump out. And one way we can sort of easily do that without, well, this actually doesn't work unless I have implemented that particular feature, whereas let me see, can I have somewhere where I can draw the flow. Yeah, erosion is also a thing. Yeah, that's the thing, is I have to back in erosion. Like I figure out the river goes through there, and then I can fake erosion. I can carve little valleys. In fact, the river algorithm will already do that. It'll build, if you try to patch a river across an empty gap, it will bring the land up to meet it. If you try to carve a river through a mountain, it will build a gorge, although I would really like it also build caves and things, depending on how tall the mountain is that it's trying to drill through. But anyway, where was I going? Somewhere I'd drawn, not those crappy pink flow lines, but when we do... I think it was part of something else, so we'll just draw the crappy pink flow lines. Yeah. There does get to be a point where I've got too much debug code, too many steps. So let's draw all this stuff, and then we'll also draw the little flow directions. So here we see, right, the general flow of water coming into this particular point is in this direction anyway. So chances are the force of this water could be strong enough to make its way over here, and then of course that's how we calculate it, but then the game would then force erode that so that there would be a sort of valley for that water to escape. And we could apply that to similar areas. The other thing I did was let me turn that off again because it's quite ugly. Let's see. I kind of hope to be coding again by this point. But the blah, 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 blah. Okay, so the other thing was, if we get to these red points, we'll look at our surrounding area, and if there's one that's got more water than we do, then we'll flow into that as well. This turns out to be not great. It was better in the old, so if we do a water check, so we'll go a little, see how this changes. Also, the order turns out to be very important, so we get kind of weird flow now because each step calculates this. What I would prefer to do is calculate all of the gravity, find out where we get stuck, then calculate all of the sea cost directions, find out if we get stuck, and then if we're there, calculate the next and see if we get stuck, or factor all of them into sort of a costs system. But we start to get interesting things. My problem with this is that what I really want is long meandering rivers, occasionally, right? Long meandering rivers that start in the mountains and go all the way to the coast, because ultimately we want those kind of river trade routes. Lots of little streams and stuff, that's fine, but I want occasionally, and this never happens right now, but occasionally I want one of those rivers to flow, to join up with the other ones and flow all the way to the coast, because that's where a town would form at the coast, almost guaranteed. Towns might dot along the river, and a town would form up in the mountains because that's where a mining town, different resources, perhaps that's a heavily wooded area and we float trees downriver to ship out, that kind of thing. You just know there's automatically a bunch of things from a world generation, lore generation that happens from rivers. They're very important. And so I want occasionally long rivers. And that's one thing we did definitely get with the cost-only form. But that's all we got, right? And that's not fair either. And we got some pretty crazy... No, that's the other thing, is like we don't automatically take a path if we've already seen it, that kind of thing. All of these have to sort of factor in. What I've been doing is laying the foundation and showing you guys the foundation of what I've got so far. What I want to do now is start thinking about what the actual algorithm will look like, because from a given place, from a given point, if we're saying we calculated the river up to the this point so far, why would I travel this way instead of hopping over to this other source that I've already started? They look like they're about the same elevation. So instead of treating these all as separate steps, first look for this kind of thing, then look for this kind of thing, then look for this kind of thing, can we build a cost, for lack of a better word, where we examine all of the neighbors and we give them a score based on their suitability? So this guy would get a higher score because he's another river source, right? So chances are we would join up to him because there's probably some kind of spring here, blah, blah, blah. But, if he's super uphill, we wouldn't. It'd flow the other way, that kind of thing. So we would generate a cost based on how downhill it is, how likely it is to flow to the sea, whether we have enough flow to overcome. So instead of treating it as separate passes, we would use all these factors to come up with a score and then pick the best neighbor from those scores. And that way, within that, you could cost things differently depending on how you wanted to play with it. And by changing those costs, we change the algorithms. I just really like that this almost does what it's supposed to do. And with some pruning, it could probably be okay. But so this was kind of a magic moment because it was the one thing missing from the rest of the algorithms, is being able to plot directly to the sea if I wanted to. And so I just feel like if we come up with that score-based search, then we can weight things. And potentially you can say, if you're further downriver, like we know we've got a lot of water coming upstream, then you weight the algorithm different here so that it's more likely to head to sea because we've got less, maybe more likely to head uphill because we've got this entire head of river ahead above us. So that was a really long explanation on where we are. Yeah, I mean, I am almost there. I think it's still a little boring. And I do want just isolated streams. It's a kind of, again, a balancing act. And even this is not too bad. I could see dealing with this. Again, these are really far distances. We're not thinking about this, right? This guy up here, like from here, like it's obvious he should flow down here, right here into this river. But we got to remember that this is a really long distance. Like these are the buildings, right? That is a really long distance up there. And there's any number of reasons it could flow in a different direction. So, way up here, this source, maybe it really did carve a little lake up here and head this direction. I don't know. I mean, I don't want to constrain it too much to physical reality because we lose some points of interest that way. But yeah, it's just tantalizingly close, right? And so how do we balance all other factors? Yeah, you can tweak it forever, and at some point I need to just decide on an approach, add the parameters in so that I can tweak them. Potentially a world could randomize those parameters, so maybe you get a world that's heavy on rivers and a world that has hardly any rivers and all streams, and based on the seed that you've used. But I need to get something workable that gives a just general variety. This is not variety. It looks wrong. So the other thing that's hard to determine from this picture is what order it actually processed them in. The way the algorithm works is that it's propagating the rivers. It starts with the highest elevation and works to the lowest elevation, so you're more likely to get flow from higher elevations. But we also could weight it to, it's more likely to work on points that have already had flow into them, and that's something we can build into the score as well. So let's think about that. because these all, again, and it's a huge combinatorial problem because every time you tweak one thing, it affects all of the other things. So for example, let's say I change the order things are processing. Instead of always just being the highest elevation first, that it's the highest elevation and also that we've fed river into it before. So it's more likely to keep building one river than to start all these little separate rivers, right? And then you make all of these guys more likely to jump over to a neighbor than it is to create its own path. Then you've done two things to affect the algorithm. Like if you had just done that, this would create a bunch of little tributaries that all form into one. But then if you also change the order things are processing in, maybe this guy was the highest elevation, so now he goes and all these other guys connect to him, and it really changes the pattern. And so now, I'm left what to tackle next while I'm on the live stream. Yeah, so it's all, a lot of playing, and I'll be spending all weekend probably playing with these values. But let's get to maybe a framework of something that gets tweakable. The thing is, there's two different approaches, right? There's so there's one approach, which is the one I've been using, where try propagating by gravity. If that doesn't work, try propagating by sea cost, basically distance to the sea. If that doesn't work, try propagating by flow direction. So that's approach one, where you treat each of these as a separate step. And whether you treat them each as a separate step, or where you're still evaluating each cell on its own for each of these things. So this cell would try gravity first, and then this cell would try whatever first. Or you're treating it where we try all of the cells and we propagate them as far as we can with gravity, and then whatever's stuck, once we've got everybody as far as they'll go, whatever's stuck, then we try propagating by sea cost, and then do everybody as far as they go, and then we try propagating by flow direction. So this is kind of approaches 1A and 1B, depending on how you do it. And then there's approach 2, which is the one I just talked about a minute ago, which is at each cell build a cost that incorporates all of those things, all factors. So gravity, rivers nearby, etc. And then you pick the lowest cost and you head in that direction. And then this is easily tweakable by different parameters, but we can see that when we talked about approach 1A and 1B up here, 1B, where we try propagating as far as we can by gravity, which is correct, right? Physically, that is correct. And then we see, can we cheat a little by sea cost for any rivers that didn't make it? Maybe we check sea cost, and then if that all fails, we try cheating a little bit more by letting them jump over cliffs and things. This one feels like it would make better rivers. Approach 2 gives me some easier things to tweak as far as parameterization. It also, because it's cost based, it allows me to say, well, if the river's higher, like if I'm further down river, I can tweak my costs differently. Or if there's a river nearby that I can easily jump over to, that gives it a cost factor. And so we just pick the best costs. But what it loses is sort of the try one approach as far as possible. And so it could be a combination of these, right? Where we first try 100% by gravity, or different cost factors, right? Maybe we do multiple passes of approach 2 where, first pass, or a combination, right? Cost-based, but multiple passes. So the first pass, we heavily bias towards gravity, and joining existing rivers. And then the second pass, we do sea cost and flow and some other things to try to cheat, the things that we couldn't get for gravity. So anyway, these are sort of the things I juggle with in my head, and so far 1A is the approach I've used. I want to play with approach 2. It gets a little unwieldy because you've got a lot of code in this file already, and so maybe I'll split off of rivers too, but I'm trying to think what things could we play with. One of the passes is pretty close to a cost. Let's do two things. Let's tweak the algorithm. So fed count, I think I never change. Yeah, so I never change fed count, even though it is considered. So these are the flow cells, and these are how they're sorted by priority. And currently it's just elevation because nobody ever changes the fed count. But the idea being any new thing that comes into us would increment our fed count. And I don't think I never hooked that up. So already we could potentially change this picture just by hooking that up. And where would link flow? So when we link one path to another, so we link a source to a target, then we always link a source to a target. We potentially remap the index, but in this case our target fed count will increment. So let me take a screenshot of this. I don't think, because we're not looking at neighboring rivers and everything operates independent, I don't think it's going to change the picture to do this, but it might, because how the rivers try not to join themselves. So we took a picture. We'll take a picture of this, and then I can compare them here. So yeah, looking at these two, you don't see that I'm hitting back and forth, or maybe you can see up at the title bar up here. If I turn back and forth, nothing changes. So that didn't really affect things because this particular layout is order independent. They're always going to pick the best paths, and they never try to join each other. But at least we're sort of preferring to build on existing rivers, which will be important once I add in, just now I'm going to add in the sort of weighted to go to existing. So we will deal with that, and one of these loops is already cost based, which is, so this is the one that takes the lowest cost to reach the sea. Well, first of all, cost only is the one we're dealing with now. We could weight this by whether the neighbor that we're trying, so basically, so we pull, so here's how the algorithm works. We've got a bunch of seeds, basically river ends that we're trying to extend. We pull one off, that's called flow. It's no longer pending. Then down here, first thing we do is check all the neighbors, and if that neighbor ID is not our ID, meaning we're not trying to join our own river, then we, you're making me want to build a river. Yeah, that's the way it goes, man. I've been thinking about this stuff for probably 30 years, and each time I attempt this, it gets more advanced. But back from my earliest days of doing diamond square algorithms and little teeny maps compared to the whole world generation I'm trying to do here. But yeah, it's always tempting because it's just so much fun to play with data like this. So here we are. So if the neighbor C cost is less than our lowest cost, which started out as our cost, then we go ahead and head in that direction. But how can we, let's bias it by if there's already a river there. So let's make a bias. If there's already a river there, and especially if it's, So the bias equals 0. If neighbor fed count greater than 0, bias, anyway, so we'll just set bias equal to 1 for now. I don't know. Maybe 10. Let's try 10. So if the C cost minus 10 is less than lowest cost, so we'll tend to prefer things that have already been fed by other rivers. So let's see what that does. We've already taken a screenshot of this, so we can compare. Let's see what this does. Oh my gosh. That's not what I wanted. I mean, it did some cool things here, right? That's not what I wanted at all. I feel like wow. So this is the fun part of yeah, so we had all these rivers feed go over the mountain. 10 might have been too high of a factor to all right. Oh, you know what? I forgot to plug in the bias. So yeah, I did like just a direct 10. So everything was always going to hit the first neighbor. Thanks for pointing that out. Right, it's funny as you pointed it out right as I saw it too. Ah, that's more of like what we expected to see, right? Of course, we lost our pre-picture, so let me change this back to 0 for a second. Yeah, I love unexpected things. I mean, that's what's so compelling about this is I will spend hours on this. This is the kind of thing like playing a game, right? Where you decide, oh, I'm going to try out RimWorld, and then you lose an entire weekend because you've played the game instead of eating or sleeping, and this is sort of the similar thing. There's always just one more thing to try, one more thing to try. Oh, yeah, it's time to put the kids to bed. Yeah, okay, just hold on a second. I'll be right there because there's just one more thing to try. So here's the boring way, no bias. Everything just goes straight to the ocean. Oh, maybe it didn't. This seems different than what we were getting before. No, okay, everything's going to the ocean kind of as quickly as it can. Lots of parallel lines. So we'll take a screenshot. Now we'll add our bias in and see what difference we get. But yeah, very appealing so far. Yeah. So that's pretty good, right? Let's compare the two. So we got this one, which is the boring one, and then this one, which creates a lot of cross. Yeah, look at that. Now, it got stupid in some cases, but again, it's promising, right? It's tempting. We do some dumb things. Here I'm looking up here. We seem to have gone uphill and back downhill again. And so I'm not sure why that happens. So that's the other thing that's yeah, it is pretty good. That's the other thing that you get a problem with when I see stuff like this. You then have to figure out, like, so we started here, and for some reason, rather than flowing to either of these, we flowed uphill and back around and back down, which is dumb. Why didn't we just flow over here? And so you have to start looking at it because is there a bug in my algorithm, or is the math weird? You know, is there something I hadn't considered about the math? But yeah, this stuff looks good, right? All these things flow into this guy who flows into here, which has other things flow, and they all flow eventually into this lake over here. And so that's kind of cool. I don't I don't know why this is going uphill here. And debugging that can be a deep process. I'll show you a little bit about that. So how would I debug this particular issue? Well, the kind of painful way is you place the ship here and you see kind of what the general coordinate is. And then I have this code here that can say we'll set debug on if we're near that particular point. 24.9, 38.49. So let's just confirm that we get a debug statement from that. Yeah, okay, so we know we'll be able to debug that particular point and see why it chose going uphill instead of choosing one of these neighbors. It's just bizarre because that neighbor should not have had any feed at all. Alright, so we got a debug set. Cost only is where we are, so we know. Let's see. If debug info neighbor. So log the location of that neighbor cell, just to be sure that we get all 8 of them or so. So we get all the surrounding ones. Why did we pick the one we picked? That's the other thing we'll have to look at. So that's where we say info lowest neighbor. Yeah, I'm starting to fade here, guys. Bias. Okay. Oh no. Oh no. Oh no. I forgot to gate it on the... Okay. Fortunately, it did finish in our lifetime. Of course, it's really gobbling up the crap. So do I kill the application and restart it and find my location? Or yeah, I think I'm gonna have to. It's unfortunate. We debugged a little too much. So now we got to get all back set up again. Oh no, I didn't save. Alright, kill it again. I appreciate that some of you guys logged in and hung out with me while I did this. And this is exactly what I'll be doing for the rest of the weekend. Yeah, it's a common developer problem, right? But yeah. So hopefully when the game is working and you guys are on a raft flowing down the river, you guys will appreciate, any of you who've watched these videos will appreciate the work that went in to making those rivers happen. I really look forward to it. That's the other thing that's cool about this development, is I know even if I fall like 50% of my vision, it will still be something that I would love to play and just explore. I already love exploring the worlds and they don't have much in them, so I just feel like yeah, it keeps me going. At that, in these live streams and you guys chipping in comments and stuff, that definitely helps me keep going too. Okay, so we're back into the realm of being able to run it in our lifetimes. So let's check, why is it going uphill? I think I turned myself, yes. So this is really, so we're going directly north. So negative z. So that would be, there it is. So we started off at 3840, 24,960. So that's the one. Why did we go up? The lowest cost at that point was 38. Our neighbor was 35. But why, before we added bias, like if I take the bias out again, this doesn't happen. Oh, it did happen a little bit. But why did it not jump over here? Why did it make it worse? Oh, what it did was it improved the cost of the bad way. No, it shouldn't. It didn't have a bias at all. Yeah, see, I do these. I'm talking out loud to you guys, but I actually talk exactly that much sometimes when I'm by myself. It's like, why did it do that? Say things out loud. Why didn't it go over here? We had no extra bias in... So we got 35 was the best. That is the one that's north. Somehow. Oh, I know what's wrong. Again, bug in the algorithm. Yeah, rubber duck debugging. Exactly right. I've even been training my oldest child that they like to bring one of their old stuffed animals down while they're doing their computer homework sometime for exactly that reason, just to kind of have somebody to bounce ideas off of, and has already heard of rubber duck debugging as well. C cost minus, so we need to include the bias in the lowest cost that we're keeping, otherwise we're not comparing apples to apples anymore. So that's the bug in that. And this should make it go jump over here instead. Yep, look at that. So again, sometimes you see wild stuff and you go, that's not right. Ooh, it's pretty though. But now things look much more sane. And so let's compare this. Let's pop out way out here. Ooh, look at that. Wow. Okay, so yeah, I can't reset the angle. Okay, so we got this. Let's try to get everything in view. Okay, so let me take a screenshot before. So we get rid of the bias. Get rid of the bias. Come on, finish. Okay, take a picture. See, these rivers are already really cool, even without the bias, because it didn't. It's these heavily wet areas that it really caused a problem because there are so many river sources. Wow, look at that river. That one's cool. All those tributaries forming. Makes me excited. These are like rolling grasslands too. That dry brown grass. Okay, so then we put the bias back in. Oh wait, let me take my screenshot. I don't know if I did. Oh, I did. I can see it down there. So we got 2 screenshots now. Okay, now we'll put the bias back in. See how that changed things. Hopefully all for the better. Take a screenshot again. And then compare the screenshots. Blink, blink. Okay, so this is no bias. We got lots of these ugly parallel rivers that look like parking lots. And then this, oh yeah. And it didn't really change these much. Except for it cleaned up a lot of these too, didn't it? Even these in the dry areas, it cleaned them up a bit. Yeah, so this is definitely the right idea. So then it's a matter of And I'm going to kind of end the stream here, and I'm going to talk about my next steps, right? We had that document up here. So I think I like the cost idea, and I think I'm going to do multiple full passes because I like that idea as well. The thing about this, so here's the other interesting thing. If you do it, if I do it in multiple passes, I can decide. So let's look over here, right? So I'm calculating rivers. First, I do a pass that just does straight gravity, maybe biased by trying to join to existing rivers if they're already there. And so then they'll all get stuck in the valleys of the world, right? And then I try the next pass, which is, using a cost-based thing to get to the ocean, but like perhaps deciding that certain costs are just too high. Like if this is my best option for going uphill here, just don't do it. Or bias that particular cost higher in the cost, bias that particular distance to the ocean cost higher than other factors. But the reason it's kind of cool is because that particular cost structure could be aware of the whole world or this whole cell, right? So, and here's where I'm going with this. Let's say I've decided that if I've already connected 5 rivers to coastlines, in this particular area, then I will lower the cost associated with reaching the sea, so that other rivers are less likely to reach the sea. So if I've calculated this big long river out and he reached the sea, and another big long river out and he reached the sea, then I make it less of a issue to try to reach the sea every time, so that other guys can just stay isolated. That's the thing I can do when I have multiple passes. If I'm doing it where every cell, basically I build a cost at every cell, I can't do that because these rivers are all being built at the same time. So the idea being that maybe some rivers using the first approach or the second pass would make it all the way to the ocean, and then so in subsequent passes where I'm trying to cheat a little more, I can cheat less because I already know, the mainland is pretty well connected to the sea and so on and so forth. So that's the nice thing about the sort of the combination of multiple passes, is that each pass could adjust its thresholds or the multipliers and things based on the results of the previous pass. So if pass 1 or 2 made it to the ocean a bunch of times, I can lower the cheating factors on the next passes. So I think this is the right idea. I mean, this technically I could, because again, we're seeing this from high up and all of these look the same distance. I mean, technically I could write a game with this right now. Take local terrain into account when this is carving in to say this river, instead of going straight from here to here, should probably meander through this little valley, and so on. And this one would have to, potentially follow through here instead of go around here. This is workable. I could write a game with this. I'm still going to play with it, of course, because that's my nature. But we're seeing it from up here. All those rivers look super stark and bright. But the thing that's important to remember is that these are really long distances. 128 meters is a long distance. That was almost the original clip of Mythruna, to be able to stand here and not even see this other point. And so, each of these little things is a block here. So this would start out as a little stream, meandering around here and get thicker and thicker until it was a river far down here. So I could probably get pretty far just with this, and I'm pretty happy with that. I will tweak it, of course, because that's my nature, as I said, and I don't like the fact that this goes uphill. I'd much rather it come down and join these guys. And see, this is the thing. I get tempted. You see this here, and yes, it would be really cool if this carved through the mountain and came this way. But what would be even cooler is if it came down and made a couple waterfalls right here. Like, it's just so tantalizing to have this river source up here and a whole bunch of really sort of dramatic rocks that it could be cascading through in a couple of hops and waterfalls that I can't ignore that, right? Um, Logically, it should flow downhill. We can see that. And it shouldn't flow over hills. So if I can tweak the algorithm to the point where I get basically all of this, but then this flows downhill, we get that. Maybe not have all of these always flow to the ocean. So again, tweaking the costs, and I think that's where I'm going to end it. We're already 10 minutes over, and I would like to do other things tonight and get back to this later tonight. But I'll keep posting screenshots as I make progress. And thanks you guys for joining. It's been really great having some folks along, kind of understanding the excitement I get when I work on these kind of weird numbers. So thanks for joining. And let me go ahead and bring up my thing so I can start closing out. Yeah, thanks for joining. Thanks for watching. Like, comment, subscribe. Share with your friends if you think somebody else might be interested in watching what I just did. This recording will be up. I may go back and add chapters later, at least bulk chapters to kind of separate me explaining what I did before from what I'm about to do. But definitely feel free to share with your friends, like, comment, subscribe, all that good stuff. And thanks for joining. I will see you guys next time.